Good evening, everyone, and hearty welcome to this Vigyan Adda series. It is my great pleasure today to introduce Professor Joseph Samuel, who is the speaker today of this series. Professor Joseph Samuel is at ICTS as Simon's visiting professor. He's a retired professor from RRI, currently working in ICTS. His research interests include general relativity, quantum theory, optics, the geometric phase, and the geometry of soft matter. He is also interested in disseminating the excitement of science and gives talks in schools, colleges, and to general audiences. A unifying theme in his work is the use of differential geometry and topology in physics. He likes to be in touch with mathematics as well as experiments. He is interested in seeing analogies between different areas of physics. One example of this is exploring the relation between surface tension and the cosmological constant. So today he is going to tell us about the finite part of infinity. Sam.
Thank you, Rukmini. I'm very happy to be able to talk to you in this forum. As you probably know, the Vigyan Adda is slightly different from a popular talk in the sense that we try to convey not only the excitement of the subject, but also some of the substance. So today you might hear a little bit more about the actual mathematics and physics that we are talking about, and not just at a very superficial level. Of course, I will try to keep it light. The mathematics which I'm going to present is actually quite deep. And actually, to be honest, I also don't understand all of it. I just understand a small fraction of it. And even that, I'm going to reduce for the purpose of this talk, to present things in an elementary manner. So the topic of my talk today is the finite part of infinity. And the motivating factor for this talk is an identity that was written down by Ramanujan, the great Indian mathematician, Srinivasa Ramanujan, and all of you have heard his name. He wrote one of the equations, one of the equations in his notebook reads like this: 1 plus 2 plus 3 plus 4, all the way up to infinity, equals minus 1 over 12. Here's the equation. Have you seen this equation before? I would like you to answer yes or no, so I get an idea about the audience I'm dealing with. There's an option on your screen. Okay, very good. It looks like at least 3/4 of my audience have seen this. So we can end the poll and carry on with the lecture. It looks like I've got an audience who's quite well informed about these things, so I can go a little bit faster probably. But I'd still like to address the 26% who have not seen this before. Okay, this equation seems wrong on so many levels. If you look at it, you're adding integers. Normally when you add integers, you get another integer. Like when you add potatoes, and if integer number of potatoes are still an integer number. Instead, you're adding integers to get a fraction. Secondly, when you add positive numbers, you get another positive number. Here you're adding positive numbers to get a negative number. Now, on the face of it, this looks like a scam. In fact, it looks very much like an investment scam. Suppose you enter an investment opportunity where you put in 1 rupee on the first day, 2 rupees on the second day, 3 rupees on the third day, and go on increasing by 1 rupee every day until the end of time. At the end of days, when you go and look for your money, when you ask the investment banker, how much money have I got there? You think you can probably retire and live on easy street. But he'll tell you, you owe me 8 paisa. So that's the kind of situation we're dealing with. Obviously, this equality is not meant to be taken literally in the sense that you apply to in the mathematics which you use when balancing your bank account. This is something different, and we need to understand what this equality sign actually means. It's certainly not a scam. And if you want to be convinced about that, you just have to look into the eyes of Ramanujan, whose intense and intense and completely dedicated devotion to mathematics would not permit any kind of scam. He was convinced that this equation is true, and there's a sense in which it's actually true. And this is the sense we're going to understand today. We're able to enter into the deep mathematics of divergent series and understand techniques which are useful in theoretical physics. And it's not only in theoretical physics. We can use these ideas of Ramanujan's to make predictions about real experiments in the laboratory. The experiment I'm going to talk about today is the Casimir Effect. It's a very strange effect that was noticed in 1948. If you take two parallel copper plates, I'm assuming them to be very good conductors, take the two copper plates, neutral, and keep them parallel to each other, and you'll find that they attract each other with a tiny force. Now, this effect can be understood by using Ramanujan's identity. This also gives you a simple example of how we make sense of infinities that appear in physical theories. For instance, in string theory, in the initial days of string theory, there was a theory called bosonic string theory. And this theory only makes sense in 26 dimensions. And the number 26 is forced upon us by this identity. Very briefly speaking, in 26 dimensions, there are 2 longitudinal dimensions and 24 transverse dimensions. And this 22 comes about, the 24 comes about because of 12 in the identity, and twice 12 is 24. So in the more recent string theories, there are more advanced versions of the same notion, but sticking to bosonic string theory, this is an example of how you can predict the number of dimensions of space-time within a theory just from using Ramanujan's identity. So the plan of the talk is as follows. The introduction should last just 5 minutes, and that's what you heard. Then I'll spend 20 minutes talking about convergent and divergent series. That's the meat of the mathematical part of this talk. Another 20 minutes talking about the Casimir Effect, which is the meat of the physics part of the talk. And then I'll wind it up with a conclusion, summarizing everything I said. Now, if there is time, I would like to get onto something more advanced in order to please the 75% who already know some of the background which I'm talking about. I may not do it if I'm out of time. If the questions are numerous, then I will have to skip the last bit. But if possible, I'd like to cover that too. Now, regarding questions, I've set up a system here by which after each of these mini parts, for example, after the convergent and divergent series, I will have a question session. And after the Casimir Effect, I'll have a question session. And finally, at the end of the whole talk, also, I'll have another longer question session. The question sessions within the talk are meant only for clarificatory questions. If you have a doubt when I'm talking, you just type in your answer, your question into the chat, and Anupam will bring it up in the mini questions sessions. And if it's a more open-ended question, that can be handled at the end of the session. I hope that is clear. Let's get on with it now. Let's look at some elementary series that you all learned at your mother's knee. There is, in school, you're taught about the arithmetic progression. And the geometric progression. In India, this is normally abbreviated as AP and GP. So the arithmetic progression consists of 1, 2, 3, 4. I mean, 1, 2, 3, 4 is an example of an arithmetic progression. And its characterizing feature is that the difference between subsequent terms is constant. In this case, the difference is 1, and you start out with 1. But you can have more general arithmetic series that start out with some other number and have a constant difference, which is not equal to 1, but something else. A geometric progression, the subsequent terms have a constant ratio. In the example on the screen, this ratio is half. So you keep halving the number before it to get the geometric progression. When you get from progressions to series, what you do is to replace the commas in the progression by the addition symbol. Now you have an arithmetic series, which is 1 plus 2 plus 3 plus 4 up to infinity, for example. Or it could even be a finite series. That's the thing we're trying to understand. And an easier series is the geometric series, of which an example is 1 plus half plus 1/4 plus 1/8. Now, the word progression is often used in school, but I think when we get to college, we're more used to calling this a sequence rather than a progression. So I will use that too. A sequence is simply a collection of numbers, A1, A2, A3, one for each integer or one for each natural number. And the sequence is sometimes written as AN, where n goes from 1 to infinity. More formally, it's a map from the natural numbers into the real numbers. Now, what we do when we're talking about trying to sum the series is we talk about the partial sums. So Sn is the sum of the first n terms of the sequence, and that's called a partial sum. For example, for the arithmetic series, you can work out that the partial sum is n into n plus 1 by 2. Now, this little slate in the corner is supposed to remind me of a story which many of you would already know. When Gauss, the famous mathematician from Germany, was in school, the teacher was one day feeling too lazy to teach. So he gave the boys a hard sum and decided to just sit down and relax. You can't blame the teacher for this. I mean, he must have been a tired, underpaid man. Now, the whole class, there was a custom in the whole class that when a sum was given to the class, each lad or lass, I guess, who finished the sum would write the answer and the working on a slate and keep it face down on the teacher's desk. So one by one, the answers started coming in. The first answer was Gauss. His answer looked just like this. It looked like 5050, no working at all. And the other children put down their slates on top of his. And they all had complicated workings. At the end of the day, when they looked at all the slates, the only correct answer was Gauss's. And the answer was done by an ingenious method. The others were, of course, using this normal way of adding up the numbers, 1, 2 plus equals 3, 3 plus 4 equals 2, whatever, keep going like that. And Gauss had an ingenious method. He just wrote down the numbers in his head from 1 to 100, left to right. Then he wrote down the numbers from 100 to 1, left to right. And he added the two sets of numbers. In each case, the sum was 101, and there were 50 such sums. So he just did a multiplication and got 5050, which was the correct answer. Now, the moral of the story is that mathematicians mathematicians have the eye for patterns, and Gauss saw the pattern. The second moral is that mathematicians are really lazy. They will go to great extents to look for patterns rather than do the hard work of adding up all these numbers. Both these models are well to bear in mind. Coming now to the geometric series, the partial sum of the geometric series is given by this formula, 1 minus r to the power of n plus 1 over 1 minus r. This is easy to derive. You write down the series from 1 to rn, and then you write it down again. And then the second time you multiply it by r. And you find you get the same series, 1 plus r, except that it now goes from, instead of 1 to r to the n, it goes from r to the power of n plus 1. Now, when you subtract these two numbers, you find that all but the first term of the first series cancels out, and all but the last term in the last series cancels out. And you get an answer, which is 1 minus r to the n plus 1 upon 1 minus r. And let me clarify here that whenever you have a finite set series, it's absolutely well defined. You can use a finite series just in the way you do your banking. It's when we get to infinite series that we have a problem. So these two series, the arithmetic series and the geometric series, are all I'm going to use today, apart from some tricks which I will use to sum divergent series. Now the question is, suppose you have an infinite series, can we assign a value to it? In fact, this is not an easy question. If you ask yourself the question literally, you take your calculator and start adding 1 plus half You'll be punching in numbers forever. You'll never get a real answer. And in fact, this problem was something that puzzled the Greeks. There's a guy called Zeno who had a number of paradoxes, all based on the fact that it doesn't make sense to add an infinite number of quantities. So he's got a famous example of Achilles and the tortoise. You have a race between Achilles and the tortoise starts with a head start, and you'll find that you never can overtake. It'll take you an infinite number of steps to overtake the tortoise, so you can never do it. That's Zeno's paradox. And let me just tell you that a paradox is a truth which is standing on its head in order to attract attention. So the paradox is presented in such a way that when you resolve it, you end up with a deeper understanding of the mathematics. Now, mathematicians like Euler assumed without too much trouble that it was possible to sum series. And of course, they were able to sum many series. Some of them were convergent, to use the modern term. Ramanujan also played with infinite series. And both of them used to play with series, whether they were convergent or divergent. So they played with series as children play with toys. Some order was imposed on the subject by Cauchy, a famous French mathematician. He answered the question, can we assign a value to an infinite series? By saying yes, if the series converges. And then he went to define convergence. So you take the sequence of partial sums, and if the sequence of partial sums tends to a limit, a finite limit, you say that the series converges. Otherwise, it does not converge. And you can easily see, looking at the arithmetic sequence, that the sequence of partial sums does not converge. It runs off to infinity as n gets bigger and bigger. The geometric series converges provided R has modulus less than 1. What you find is that the term r to the power of n plus 1 gets smaller and smaller and smaller, and the partial sum converges to 1 upon 1 minus r. And this is the problem that bothered the Greeks and Zeno in particular. And Zeno's problem is solved because Cauchy introduced the notion of a limit, which did not exist in the Greek times. So we are going to slightly higher mathematics now by using notions of limits. Here's a simple geometric way to sum up the geometric series. I take the series 1 plus half plus 1/4, which I've written in different colors up to infinity. Then 1 is represented by a square. Half is represented by half the square, and 1/4 by 1/4 the square. You can see that geometrically, you're going to fill up the whole of the 2 squares and get your answer 2. So the geometric series does converge for R modulus less than 1. It has to be strictly less than 1. Now, Ramanujan is one person who did not respect these boundaries. The boundaries are that there's a problem when R hits 1 or minus 1. I'm only dealing with real numbers for a lot of this talk. I won't go complex because out of consideration for the high school students. But Ramanujan is also one to push boundaries. Let R approach minus 1. Take the same identity and take the limit where R goes to minus 1. The right-hand side becomes 1, minus 1, plus 1, minus 1, up to infinity. And that is a series that's called the Grandi series. That's why I've written the sum as SGR. And the left-hand side goes to 1 upon 1 minus 1, and that works out half. So according to Ramanujan, the sum of the Grandi series is half. I can do this a little bit more formally. Instead of just taking the limit of R going to minus 1 and plonking it down in the equation, I can actually replace the original series minus 1 to the n by minus 1 to the n minus exponential of minus lambda n, where lambda is a small positive number, which brings the ratio slightly less than minus 1. I mean, the mod of the ratio slightly less than 1. Let lambda tend to 0 from positive values. And then you find you get the same answer. You get 1 upon 1 plus e to the power of minus lambda. And when lambda goes to 0, you get half as this answer from this series. Now, this is interesting because there was another summation method due to Cesaro. What Cesaro said is that if I'm given an infinite series, I will look at the sequence of partial sums and take the average of the sequence. And if you look at the partial sums of the Grandi series, you find it rattles between 0 and 1, spending equal time in both these places. And if you define the average in some formal and simple way, you find that the Grandi series will sum up to half, according to Cesaro's method as well. So perhaps that gives us some confidence to go ahead. So let's write out the geometric series, S going as 1 plus R squared up to infinity, equal to 1 minus 1 over R. And consider the product of itself with itself, that S with itself, S times S, is 1 plus R squared up to infinity, and the same bracket repeated once, half squared, which is 1/4. On the right-hand side, you get 1 over 1 minus R squared equal to 1 plus 2R. All I'm doing is collecting the terms with the same number of R powers, 2R plus 3R squared plus 4R cubed, all the way up to infinity. Now I let R tend to minus 1. And I find that 1/4 is equal to minus 2 plus 3, minus 4 plus 5, etc. All the way up to infinity. So here's Ramanujan's argument. He wants to sum the series 1 plus 2 plus 3 plus 4 plus 5 all the way up to infinity. So similar to what we did with the geometric series, he multiplies it by 4, okay, for reasons that will become clear. And he writes down the same series again, except now he writes down under alternate terms of the original series. Under 2, he writes 4, which came from multiplying 1 by 4. Under 3, he writes nothing. And under 4, he writes A, and it goes on like that. When you take the difference of these two, you find that 1 becomes 1, 2 minus 4 is minus 2, 3 becomes 3, and 4 minus 8 is minus 4. And it goes on like this. So you get alternating signs in the original series. And we know that this sum is equal to minus 1/4, plus 1/4. Now you just solve for SR and you find Ramanujan's famous identity, 1 plus 2 plus 3 plus 4, all the way up to infinity, equals minus 1/12. So that is a moment to pause. And you've seen that from very elementary arguments involving just the arithmetic and the geometric series, you're able to arrive at Ramanujan's identity. He proved it roughly like this, using a combination of intuition and deep insight. Both things are necessary. Another way to do the same thing, slightly more formally, is to force convergence. That is, we replace the original sum, which is 1 to infinity of n, by n times e to the minus n lambda, where n lambda is a convergence factor, which is designed to make the series more convergent. It's called a regulator. So the sum can be easily done. You notice that if you just write down the geometric series with e to the minus n lambda and differentiate with respect to lambda, you get the term of interest with a minus sign. So you put f of lambda is equal to minus of that, and you perform the sum and then you differentiate. It's all very elementary. And you get 1 over e to the lambda minus 1. Now you're interested in this quantity as lambda tends to 0. Of course, it blows up, but you can do an expansion around lambda equal to 0. You find that there's a first term, which is 1 by lambda squared, which clearly goes to infinity as lambda goes to 0. And next to that, there's minus 1/12. And there are higher order terms which will vanish when lambda goes to 0. Now, when you look at this term, the term in yellow here is 1 over lambda squared, and that is infinite. The term in red here is minus 1/12. And that is what Ramanujan called the constant of the series. All the higher order terms like lambda squared and higher order stuff will all go away when you take lambda equal to 0. So it has a divergent part, which is 1 by lambda squared, and a finite part. This minus 1 over 12 is the finite part of infinity, which gives this lecture its title. Now, we've come quite a long way in a short time. I must also caution that there is a great possibility of error when you're manipulating divergent series. So here's a statutory warning. Manipulating divergent series without a valid license can be injurious to your mental health. For example, if I take the Grandi series, I can group the terms by taking the first and the second term together, and then I get 0 for the sum. I can also group it in a different way by taking the second and third terms together, and I'll get 1 plus 0 plus 0, and I get this equal to 1. Now, if you interpret the equality signs in the same way that bankers do, you'll find that there's a contradiction. 0 is equal to 1. And a contradiction is something disastrous in mathematics. It's acceptable in other walks of life. For example, in our lifestyles, all of us have internal contradictions. There's a contradiction between your desire to eat, well, good meals, and also your your desire to be healthy. It's a problem that all of us have. So contradiction is part of everybody's life, but it cannot be a part of mathematics. It can be a part of poetry. There's an American poet called Walt Whitman. He said, do I contradict myself? Very well, then I contradict myself. I am large, I contain multitudes. Well, mathematics is not large enough to contain multitudes. It cannot contain contradictions. In fact, a contradiction in mathematics is essentially the equivalent of a train wreck, which is what you see on the left-hand side. It means that the entire structure collapses. Once you have a contradiction, you can prove anything you want. So the aspiration in modern mathematics is to write down a set of axioms which you believe is consistent and derive the consequences from it. So this model is basically what was given to us by the Greeks. Euclidean geometry has a set of axioms which they take as postulates or axioms, and all the theorems derive from there. And there's no internal contradiction in the system of Euclid. It would be impossible if there was a contradiction to prove any theorem, because given a theorem, you can prove an alternate theorem in which the first theorem is false. This is like in fake news today, you hear about facts and alternative facts. Mathematics cannot stand the contradiction of having theorems and alternate theorems. In fact, the philosopher Burton Russell, who was a philosopher interested in the foundations of mathematics, he's very fond of saying that given a contradiction, one can prove just about anything. In fact, he was so fond of saying this that he repeated himself often, and his friends grew heartily sick of him. So finally, one of his friends who had got sick of Burton boasting that you can prove anything given a contradiction, he gave him a challenge. I'll give you that 1 equals 0. Prove to me that you're the Pope. So Burton Russell gamely rose to the challenge, and his replies came thick and fast. So here's the argument. Right, start with 1 equal to 0, add 1 to both sides, you'll get 2 equals 1. I am 1 and the Pope is 1. Together we are 2. But 2 equals 1, so the Pope and I are 1, QED. To avoid contradictions, one needs a consistent theory of divergent series based on general axioms. And one such theory is given by complex analysis and analytic continuation. So the theory of complex analysis is often, well, I don't know if kids learn it in school, but they certainly don't learn about analytic continuation. That's something I'd like to avoid using in this talk, although it would have been helpful. But let me just say very briefly that there are things called complex numbers. And if you look at this formula for S as 1 upon 1 minus R, the sum of the geometric series, you can take a complex number R. When you write complex numbers, you change the R to Z. And note that this is a function which is well defined all over the complex plane, except at R equal to 1. So although the series is not well defined, you can define the series to have the value given by the left-hand side, which is defined all over the complex plane. That's one way of thinking about analytic continuation as a way of defining divergent series. Okay. Now, there's a very famous function called the Riemann Zeta function. And it's defined by the formula, sum over all the integers, 1 upon n to the power of s. Now, this is a very famous function, and it's got deep mathematics about prime numbers hidden inside it. We're not even going to enter into that. We're just going to look at it as an infinite series. This infinite series, well, first it was defined by Euler. Euler defined it only for integer values of S. And there also there's an interesting bit of mathematical history. When S equals 2, this series is the famous Basel problem. Basel is a city in Switzerland where Euler lived. Well, in his early days, he lived there. Later, he moved to Petersburg. And it was a challenge to sum this series up to infinity. The sum was finally proved to be pi squared over 6 by Euler himself. And all the higher S integers also, I mean, there are many values for which it is known, the sum of the series. For S equal to 1, this is called the harmonic series, and it diverges. And for S equal to 1, this series does not converge, not just at S equal to 1, but for the entire plane where the real part of S is positive, is greater than 1. So half the plane, the half where S is greater, the real part of S is greater than 1, this function is well defined, and it diverges on the left half of that straight line. If you draw a straight line through 1, which is vertical, on the left half it diverges, and on the right half it converges. But you can use this to define divergent series for all values of S except for S equal to 1. Now I'll pause for questions, and let me see what is going through your minds before I get into the physics part of this talk.
Yes, Professor Sam, so there is a question by Kavya. She's asking, does rearrangement of the terms not affect the Cesaro convergence?
No, Cesaro convergence is not affected by rearrangement, but some of the other terms, I did some grouping of the Grandi series. Such things can affect the final answer that you get. So changing the grouping is not allowed if you have series which are not, okay, let me just say one more thing. There's a notion of absolute convergence. There is series which converge even if you replace every term by its absolute value. They have slightly better behavior than series which have alternating signs. So if you have absolute convergence, you're allowed to do mode manipulations. So there's an elaborate set of rules which you have to follow when you manipulate series. And in this instance, Cesaro series is not affected by changing the order.
Thank you.
Any more questions? That was
yes.
covered, right?
Yes, so Agnish has a question. Can we use this similar argument while summing bigger infinities with the small one?
I'm not sure what you mean by that. The theory of infinities, this will take us slightly off topic. Cantor is the person for looking at different kinds of infinities, and we're going to only stick at very basic parts of that problem. So I'll postpone Agnish. Maybe we can discuss it later.
Yeah.
If there are no questions, I'll carry on then, because I think I'm running on time. This was my budget.
Please continue, Professor Sam. We'll take these questions at the end then.
Yeah. Okay, now we'll get to physics and the Casimir Effect. The physics I'm talking about is some quantum physics, some very elementary quantum physics. The simplest quantum system you can think about is the simple harmonic oscillator, and all of us know and love this problem. We grew up on it. A harmonic oscillator is just a spring with a mass attached to it, and classically, it has the lowest energy when the mass is at rest at the bottom of the harmonic potential. So then the kinetic energy is 0 because it's at rest, and the potential energy is at 0 because it's at the bottom of the potential. Quantum mechanically, such an energy state is forbidden by the uncertainty principle, because the uncertainty principle tells you you cannot have 0 position and 0 momentum at the same time. It violates the uncertainty principle, which tells you that the product of the two uncertainties has to be at least h bar over 2. So the 0-point energy of the harmonic oscillator is not 0, but h bar omega over 2, where omega is the frequency of the oscillator. Now, whenever you see an equation in physics, you should always check its dimensions, and I urge you to check that this quantity h bar omega by 2 does have the dimensions of energy. H bar has the dimensions of energy times time, and omega is the inverse of time. So the times cancel out and you have energy. Okay, now let's take a bowstring. What I'm going to do is to introduce the Casimir effect by means of a mechanical example, because I suspect that many of you are more comfortable with mechanics than with, electromagnetic fields. We have no intuition for mechanics, so I'm going to use a mechanical example to bring out the idea behind the Casimir effect. Look at the picture of a bow here. The bow is tight, or taut, as they say, in English. The bowstring is pulled tight, and this is the kind of bow that Rama would have strung when he was supposed to win his bride. So this is the bow where the elastic energy of the frame keeps the bowstring under tension. Now, when you pull the string, the frame bends slightly, and the two ends of the bowstring come together slightly. So pulling the string away from its equilibrium position gives an attractive force on the two ends of the frame. And it doesn't matter which way you pull the string. If you pull the string away from the bow, the ends come together. If you push it the other way, also the ends come together. And I will show you this in a minute with the bowstring. In the other white slide, you can see that any string has got different modes of vibration. Right at the bottom, you have the fundamental, which is the lowest frequency with which the string can vibrate. Next is the first harmonic, which is twice the lowest frequency. Then the 3 times the lowest frequency and 4 times the lowest frequency. Each of these is called a mode of oscillation of the string. And in fact, even a bowstring has all these modes of oscillation. After the arrow leaves your bow, the string will keep vibrating, and it will vibrate in all these modes. Each mode is an oscillator, and there are an infinity of modes. And it is clear that when the string is vibrating, there is a force which is pulling the ends together. So let me just show you both these effects. I'm going to stop sharing screen and show you these demos. Here's a bowstring. This is a homemade bow. I just made it from things in the garden and some string. Of course, it's not a patch on the string that Rama used to string. It's not a patch on the bow that Rama had. But you notice when I pull the string, the two ends come together. I'll move back a bit. The two ends together come together. And when I pull it this way also, the two ends come together. And when it's vibrating, you can be sure that the two ends have an attractive force between them. I also want to demonstrate the different modes of the string. And here I will now use a different string. This is a guitar string. So I'm going to play the lowest note, lowest string here. That's the mode of the fundamental. Here's the second harmonic, third harmonic, fourth harmonic. So that was 6 different harmonics. Now I've convinced you that a string which is vibrating pulls the ends together. Now, let us let the string come to rest. Then there's a certain amount of tension in the string. But we know that if the string is classical, it can be at rest and there's a certain amount of tension. But what if there's a temperature in the room? We know that at any finite temperature, the string will vibrate with an amount of energy which is given by kT per mode. Every mode will have an energy of kT. And there's an infinite number of modes. So these infinite number of modes with an energy of kT in every mode are going to have an attractive force on the two ends. That's because a vibrating string exerts a force, attractive force on its endpoints. And the vibration is not in our control, it's because of the thermal effects. Now, suppose we cool the room down so that the string comes to 0 temperature. We don't have to worry about thermal vibrations anymore, but we still have quantum fluctuations. These are beyond our control. Even at absolute 0 of temperature, there is a set of quantum fluctuations, and that is h bar omega by 2 in every mode. And there's an infinity of modes. Now look what happens. Yeah, I should just go over some mathematics related to the modes. The fundamental frequency comes at Cs into pi over L, where Cs is the speed of sound. Cs squared is given by the ratio of the tension in the string to the mass density. That is to say that mass per unit length. Square root of T over rho is the sound speed, and the frequencies are given by Cs times pi over L. And I want you to make it a regular habit. Whenever you see a physics equation, check the dimensions. This does indeed have the dimensions of frequency. And the harmonics come as multiples of the fundamental frequency. Omega 1 is the fundamental frequency, and omega n is n times that. So you'll find that it is n times speed of sound into k1, which k1 is pi over L. So the energy in 0-point motion is h bar cs over L times pi times the same series that Ramanujan was trying to solve. Now you can see that there's a disaster looming. Here also you should check the dimensions. See, if you take h bar, it's got the dimensions of energy into time. The sound speed has got the dimensions for velocity, which is length over time. And you can see that the two lengths cancel out, the two times cancel out, and you get something with the right dimensions. But you'll see now that there are two disreputable things about this formula, which we derived from just fundamentals. Suppose I were to take this whole constant and just plot the L dependence, it looks like this. The energy is steadily decreasing with length. That means that the force at the ends of the string is actually repulsive. The vacuum, the set of all modes, each mode seems to enter and pull an attractive force together. But the final effect is a repulsive force pulling the ends away from each other rather than towards each other. What is worse is that the coefficient there is infinite. If you remember, the divergent sum here is, well, before we applied Ramanujan's tricks, it is infinite. So you have an infinite repulsive force here. That looks like a disaster. Now, there's a problem that the answers seem to diverge and have the wrong sign compared to our physical intuition about the ends being pulled towards each other. Now, I told you earlier that there's an infinite number of oscillators, one for each end, for every mode of the string. Now, that is not quite true, and which is why you should never believe what I tell you. A real string consists of a finite number of atoms, and the total number of degrees of freedom is finite. So it's a bit of fiction to say that there's an infinite number of oscillators in the string. There's just a finite number. So the sum does not extend from 1 to infinity. It extends only up to a wave number when n over L becomes of the same, well, when the wavelength of the oscillator, when the wavelength of the waves becomes of the same size as the interparticle spacing, interatomic spacing, there are no modes anymore. So there's actually a finite cutoff here. You don't have to sum over all the infinite modes. You only have to sum up to a certain time. You only have to sum up to a certain value of n. So it's not really an infinite sum. It's a very finite sum. And we can enforce the finiteness of the sum by introducing a regulator. So what I've done is to take the earlier expression and replace n over L by the same exponential factor which was used earlier. And then you get a factor which is infinite, which is here in yellow, h bar c over lambda squared pi L over lambda squared. And you get in red minus 1 over 12 h bar c s pi over L. Now let's forget about the divergent term. We'll throw it away because that's what Ramanujan tells us to do. And we replace the sum by this finite constant, which Ramanujan called the constant of the series. And we, of course, we throw away all the higher order terms because they vanish in the limit that lambda goes to 0. And then we find that the graph turns around. It's now an attractive force, and it falls off as 1 upon L squared, because when you differentiate, this is the energy. When you differentiate the energy, you get 1 upon L squared. In our experiment, we're only measuring forces. We're not measuring energies. Only differences of energy count. And let's ask what happens when L goes to infinity. You define x equal to n over L, and then dx equal to 1 over L, and this goes to 0, which means that the infinite sum becomes an infinite integral. And we find that this infinite integral is also divergent, and it exactly cancels the divergent term in the sum. So we only have the finite term, which was in red, and not the infinite term, which is in yellow. So the difference is finite and now has the right sign for an attractive force. Now, I've given you the complete argument. Now, I want to change from the mechanical system, which I thought would aid your intuition, to an electromagnetic system. So the thing that you see in yellow on the screen with the two red ends, that thing is supposed to be a waveguide. It contains electromagnetic waves. The yellow part is made of copper, and also the red ends are also made of copper. Only the red ends, the red end on the left is fixed. The one on the right end can be moved slightly, and you can use that motion to estimate the force of it. Inside the waveguide, there are electromagnetic fields, which also can be thought of as oscillators, just like the modes of a string. So the modes of a waveguide are just like the modes of a string. There's an infinite number of them to start with. Okay. And each mode has a 0-point energy given by h bar omega by 2. The argument which I'm going to present here, which I presented for the string, carries over identically to the present context. In fact, I think you may have noticed there was a small 2 in the corner, in the right-hand corner. The string has actually got 2 modes of vibration. It can vibrate in both. If the string is going along the x-axis, along the z-axis, you can vibrate in the x plane as well as in the y plane. So there's a factor of 2, which is why I canceled out the h bar omega by 2, and you got 2 numbers there. And in the same way, for the waveguide also, light has got 2 polarizations. Electromagnetic waves have got 2 polarizations. And there's a factor of 2, and you get exactly the same sum as you got for the string. And once again, you should ask, what happens? What stops the sum from going to infinity? The answer is very simple. Very high frequencies like X-rays and gamma rays pass clean through the ends of the tube as well as the copper tube. They don't see the tube at all. So they're not constrained in any way by the infinite conductivity of the tube. It's only the low frequencies which are obliged to be contained within the tube. And so once again, you have a cutoff at the atomic spacing. The spacing between the atoms of copper tells you that there are no modes which are higher than this. Actually, the cutoff comes much earlier. When there are high frequencies and the frequency is too high to excite electrons inside the copper, then itself, the copper becomes completely transparent. And you get a finite answer, which is an attractive answer between the 2 ends. So this was again done in 1 dimension. You may notice that I'm simplifying matters by sticking to 1 dimension. A similar calculation applies in 3 dimensions. The only difference is that instead of sum over n, we get sum over n cubed, which is the Riemann Zeta function evaluated at -3. That is a different number, but the general principle of the calculation is the same. if I look at the figure on the left, I see two parallel plates. And outside the plates, you see all possible modes. And all these modes have a repulsive effect, which are pushing the plates towards each other. Between the plates, you have a fewer number of modes, which are also exerting a repulsive effect. But the difference between them is an attractive effect because the outside repulsion exceeds the inside repulsion. So the net force is actually an attractive force. The two plates are pulled towards each other by a force given by the formula h bar Ca pi squared upon 240 L to the power of 4. Now, this is a very strong function of the separation between the plates. And it really becomes important to have a large area. It's a small force, but if you have a large area, you can magnify the force. And this has actually been measured in the laboratory. So I'll start with the history now of the measurement. But before that, let me just say that the exact form of the regulator is not important. I used e to the minus lambda n. There's a trick called the Euler-Maclaurin series, which gives the difference between the sum and the integral in terms of a series. And you can use a number of tricks due to Euler, integration by parts, and using Bernoulli numbers and their properties. You can show it doesn't matter what the function f is, as long as it's one. I mean, the function should be counting all the low frequency modes and ignoring all the high frequency modes. The exact form of the regulator is not important. You get the same answer. Now, the experiment was done in 1958. Actually, the theory was proposed in 1948 by Casimir, who was actually looking at colloidal systems and the attraction between colloidal particles. And he gave the theory for electromagnetic systems, unlike what I told you is for mechanical systems. Sparney tried to measure it in 1958. But when you take large parallel plates, it's very hard to keep them parallel to each other. What happens is that the distance changes as you go along the plates. And since the force is a very strong function of the separation, you get large uncertainties in the force. And he got practically a very large uncertainty comparable to the effect he was trying to detect. But he did say that it was not in conflict with the theory. The next detection was by Lamoureux. He used a plate and a sphere. If you have a plate and a sphere, the problem of keeping them parallel doesn't arise. You have a large radius sphere, which is approximately a plate. But now you don't have a problem of keeping it parallel. And he used the torsion balance to measure a tiny force. And he measured the effect with 5% accuracy. Next detection was by Mohitdin and Roy, Anushree Rai, who is actually at IIT Kanpur right now. Anushree Rai is there. In 1997, they used a plate and a sphere, just like Lamoureux. They got a better accuracy by using an atomic force microscope. So they measured it to 1% accuracy. And since then, there have been more refinements. The effect is definitely there. Now I'll pause for questions. And yeah, I think I will have to skip let's have some questions now about the experiment.
Sam, no one has submitted a question regarding the physics part yet.
Okay. So I presume it was very clear.
I think so, yeah. But
okay.
Maybe in the next section, people can feed in their questions.
Maybe it'll come at the end. So then maybe I'll skip to the part about surface tension and cosmological constant. Okay. Maybe I'll be able to finish with, I think I'll finish in time. We started at 4:35. I've got about 9 more minutes. I'll finish it. So we started with the mathematics of divergent series. And then we talked about the physics of the Casimir effect. We chose a simple mechanics example. And I claimed that the same ideas work for the electromagnetic field. Quantum fluctuations have energy. And thermal fluctuations also have energy, except that the counting is different. Instead of h bar omega by 2, you measure k Boltzmann T for each mode. And the derivative of the energy gives the Casimir force. Then we computed the difference between a sum and an integral. And let's get a closer look at the integral. I had told you at that time that we don't measure, we don't measure energies in the laboratory, we only measure forces. We only measure differences of energies. Now that was another lie. The fact is that we can measure energies, but it takes some very specific experiments. The reason for that is that energy has mass, and mass gravitates. So when you consider theories where there's gravity, when you do experiments with gravity, for example, the attraction between the mass of the Earth and the mass of the Sun is a very measurable effect. So one can measure energies, one can measure masses, except that the experiments you need are more subtle. Yeah, this is a cartoon due to Roshni Samuel, that's my daughter. So the energy has got mass because of E equal to mc squared, which was written down by Einstein. Now let's work out the integral, which I talked about. We'll start with a simple example. The thermal fluctuations of a membrane. Just like a string, a membrane can also vibrate. You've seen membranes all around you. Your eardrum is a membrane. Drums are membranes. In the body, there are lipid membranes, which consists of hydrophilic molecules which congregate together. Cell walls are also membranes, and they are very special membranes in letting in certain elements into your cell and keeping out others. Certain molecules are allowed and others are not. A drum has different modes of vibration, just like a string. So there also one can talk about the Casimir force. Now, suppose I wanted to work out the Casimir force at a finite temperature. I would integrate over the modes, supplying kT of energy per every mode. The sum over modes, now it's very easy. It's an integral over d2x and d2k, where x is the wave number and x is the position on the drum and k is the wave number. This is not a sum, but I'm just writing an integral for it because I'm looking at the integral quantity. And I'll just forget about all the 2 pi's and all that. I'll write that it's equal to the area times, the area comes from the integral over d2x. kB2 is a constant which I can pull out. And I have a divergent integral which goes from 0 to k, 0 to lambda of k dk. I can evaluate this and get an answer which is a surface tension, which is the energy per unit area. And that works out to kBt over lambda squared, where lambda is the cutoff. That is to say, it's the wave vector beyond, there are no degrees of freedom. And in that case, that's about the intermolecular spacing. Now, when I put in the numbers, kBt at room temperature is about 1/40th of an electron volt. It's easy to check that. And the intermolecular spacing is about 3 × 10⁻10 meters. And it turns out that the surface tension of a membrane, no matter what the membrane was, the fluctuations of the membrane will give rise to a surface tension, which is about 40 millijoules per meter squared. And this is roughly the right order of magnitude for the oil-water interface. So you can see that a crude argument actually predicts the right order of magnitude for the surface tensions that you encounter. The oil-water interface is about 32 millijoules per meter squared, which is very close. To extract a finite answer for the Casimir effect, we invoked 2 main ideas. The first was the atomistic nature of matter, the strain, the waveguide of the plates. The second was that the differences of energy are only measured. Now, in this experiment, the Casimir force was measured, not the energy, but that is only true of that experiment. There are other experiments that can actually measure the energy of the Casimir force. That's what I'll come to next. Let us take the energy and realize that it has got a mass and therefore it's got gravity, or rather, in a theory of relativity, energy itself gravitates. The integral we subtracted was apparently divergent, but made convergent by the atomistic nature of matter. And it had a gravitational effect. So the atomistic nature of matter is really finite, as all physical quantities should be. Now, if you take the vacuum energy of space, which is given by the integral, and you just compute it, you'll find that the energy density is given by...
Sam?
Yes?
Excuse me. I think we missed a few lines of yours when you were... Yeah, if you could repeat. Yeah.
Okay. This slide was okay?
The previous slide, from the previous slide. Yeah.
Okay. Here, it was just a slide showing that energy has got mass, illustrated by a cartoon, and that mass gravitates. And therefore, if you do experiments with gravity, you can actually measure the Casimir energy, not just the Casimir force. So the integral we suspected can have gravitational effects. So we have to now look at the gravitational effects of the Casimir energy. And a simple calculation shows that the vacuum energy of space is repulsive, and it has described by a formula h bar c upon lambda to the 4, which you can check is dimensionally correct. It's energy per unit volume, where lambda is the cutoff. Now, in all modern theories of quantum gravity, the atomistic nature of space-time at a fundamental level is believed to be at the Planck length, which is 10 to the minus 35 meters. It's an extremely tiny length. So if you put in this number, you find that the theory of Casimir Effect predicts a cosmological constant, which is also a repulsive effect, a repulsive force that accelerates the expansion of the universe. Now, this is actually seen experimentally. That is to say, astronomers have discovered that the expanding universe is actually accelerating in expansion. So the effect that's predicted by the Casimir energy is actually seen, but the value is 10 to the power of minus 120 times the value predicted by theory. It's that much times smaller. So why? This is one of the big mysteries of theoretical physics, and it's a wide open problem for the physics of the 21st century. And I'm hoping many of the people who are in the audience today will look forward to solving this mystery and taking the subject forward. So with that, I'd like to thank you for your attention. And I think I finished with about just a minute to spare. We can take some questions now.
Thank you. Thank you, Professor Sam.
Thank you so much, Sam, for this wonderful talk. I just wanted to have, I had a small comment. I think this summation n is equal to minus 1 over 12.
Yes.
This was not, it was done by Ramanujan independently, but I think it was already known in the literature.
Yes, yes, that's correct.
Minus 1 equal to minus 1 over 12.
Yeah, right.
Yeah.
There were other people playing with the infinite series, including Euler and also Bernoulli, I think, and maybe also Jacobi. And of course, Grandi. There were many people. It was a fashionable thing because before Cauchy, there were no rules of the game. In a sense, Cauchy brought in some rules, which have, if you follow those rules, you won't get into trouble. But all these people were working outside the framework. And that's why they were able to discover interesting physics, because the rules had not yet been formulated in the pre-Cauchy era. Let me just stop sharing so that I can take the questions better. Just a minute. Yeah, thanks, Rukmini, for that comment. That was very appropriate. Yeah. Let me stop sharing screen. Yeah, can you, right. So we can take some more questions.
Okay, Professor Sam, thank you for the wonderful talk. So there are very few physics related questions, so I would start with that. So Ashik asks, sir, how can we explain the repulsive Casimir force?
Yeah, actually, it is not very intuitive. So if you, see, I'll have to give a slightly more advanced answer to this. Within the theory of relativity, there's a notion of a vacuum. And the vacuum is Lorentz invariant. Now, if you look at any kind of energy density that is Lorentz invariant, it has to be proportional to the metric tensor. So if you compute the energy density and the stress energy tensor of the matter, and it is Lorentz invariant, it has to be proportional to the metric tensor. And that's exactly the form that the cosmological constant takes. So Einstein wrote down an action where there was actually only a curvature term and no volume term. There was no term proportional to the volume. So that term comes because of relativistic invariance. And it's exactly proportional to the metric tensor. And in in relativity, it causes a repulsive force. The cosmological constant, a positive cosmological constant, causes acceleration of the universe. It is a kind of anti-gravity. And it comes out of the integrals very clearly. The ones that you saw, you can clearly see that it was a positive number multiplying. You saw it when we took the initial string itself. that the divergent integral was, the divergent sum suitably cut off at the atomic scale was actually a repulsive term. The integral was repulsive, yeah.
Okay, thank you, Professor Sam. So Lakshmi has a question. Lakshmi Verma, she asks, so potential energy we define with respect to some reference point.
Yes.
So mass also depends on that reference point because of energy mass equivalence. That's a question.
Okay. So it is true that energy in the laboratory is always measured with respect to some reference point. Because when we do work, we lift a weight through a certain height, and the difference between the two heights is mgh. It's the potential energy that we supply. But if you apply that logic to gravity, it breaks down. The force of attraction between the mass, between the Earth and the Sun is absolute. It actually depends on the mass. For example, if the mass of the Earth is 0, there is no attraction. If I take the limit of the mass of the Earth going to 0, there is no attraction to the Sun. And if I take it to be positive, there is an attraction given by m minus 0. So the zero of energy is fixed by gravitational physics. So for example, if I have no energy at all, space-time would be flat. But if I have a finite amount of energy, space-time would be curved in a relativistic theory. I hope that's clear. So that's why I made the difference between gravitational physics and non-gravitational physics, where the energy has got only a relative importance compared to relativistic physics, where it has an absolute significance.
Okay. Thank you, Professor Sam. So there is another physics-related question from Shaunak Mishra, and he asked, I'm Shaunak Mishra from Jamia Millia Islamia. I would like to thank you for such a wonderful talk. So my question is, has Ramanujan summation been employed in the past or present by the physics community in the domain of QFTs, akin to the usage of bosonic string theory as mentioned, or unification purposes? This is the question.
Oh, yes, there are many applications of this in quantum field theory. So what I was doing was basically giving you the simplest example, which I thought you could understand. So the fact is that in quantum field theory, there are infinities that come up all over the place, okay? And making sense of these infinities is a very difficult problem. And it's also a very worthwhile problem, because after making sense of these infinities, you're able to make very precise predictions about quantities which can be measured in laboratories. In fact, the best measurement of any physical quantity is called the anomalous magnetic moment. That quantity diverges. And after you apply these techniques, you can compute the value of the anomalous magnetic moment of the electron and the muon, for example. For the electron, you can compute it to about 12 decimal places, and is measured experimentally to about 9, and it agrees to all those 9 places, maybe more now. Okay, so the making sense of the infinities of quantum field, important business. And I wanted to give you a glimpse into that subject by taking the simplest example and giving it here. So, for example, the Riemann Zeta function is used in blackbody radiation. It is used, it appears in Bose-Einstein condensation. And, of course, in mathematics, it appears in the theory of prime numbers and the distribution of primes. And, there are many applications both in physics and mathematics of all these deep ideas. So I think that's enough of an answer for the moment.
Thank you, Professor Sam. So I'll now transition to some maths questions. So Preetham Kumar asks, does our answer depend on the form of the regulator we use to calculate the finite part of the series?
No, it does not. And I made this point earlier. The regulator, which I chose, was convenient because you'd actually evaluate the sums as just geometric series. Instead of e to the minus lambda n, I could have put e to the power of minus lambda squared n, for example. Or there's any number of terms you can choose. There is other ways of regulating it. So the general argument relies on the Euler-Maclaurin series. So what happens is that when you use an arbitrary regulator, you can do integration by parts and resolve the question into 2 parts. One acting at very low frequencies, where the regulator is basically 1. Another part acting at very high frequencies, where the regulator is 0. You choose any function that is a function of n or x, goes from 1 to 0 at 1 at finite values, at small values, and 0 at infinite values. And the integration by parts takes care of the fact that you're only looking at the properties of the regulator near 0 and near 1. So a wide range of regulators all gives you the same answer. Otherwise, this would not be it would not be a meaningful answer, because the form of the regulator would decide many things. And even in quantum field theory, they use techniques which are extremely shady mathematically to produce finite answers. Many of them are based upon this handling of infinities by a common. There are two different ideas. One is regularization, and the other is renormalization. Both these are used in quantum field theory to come up with finite predictions out of apparently nonsensical answers. And you should understand also that mathematics in the making, or physics in the making, is not a complete finished product. It's not all sewn up and tied up with ribbons. Just like oil used to play in mathematics with very dubious stuff, like infinite series that do not converge. At some point in the development of the subject, these ideas get formalized. And finally, for example, Cauchy did that for infinite series, and maybe Cantor did that, and Dedekind, people like that did it for other kinds of infinities. And they come up with rigorous systems of axioms, which are rules which can be followed safely. But there are many rules which are broken by mathematics in the nascent stage is not always rigorous, but it sometimes leads to rigorous results in the future. So breaking rules is probably not such a bad idea. It's a similar thing with grammar. When you speak grammatically, you're following stringent rules, but grammar was invented by grammarians in order that you don't speak, but you speak with accepted grammar. But often grammar changes over the years. When more and more people use wrong grammar, after a while it becomes a grammatical rule that the wrong is right and so on. Or rather, they invent the rules that make the grammar right. So in some future part of mathematics or physics, it may be possible to come up with a more precise way of fixing all these apparently shady mathematical calculations.
Thank you, Sam, for this interesting answer. So there is a question by Akash, and you touched upon renormalization. Akash asked, my question is regarding the series of -1/12 you talked about.
Yes.
Is it same as renormalization, where we throw away the divergent part and only keep the finite part?
Yeah, actually, the regularization is the use of that e to the minus lambda n to curve infinities. The renormalization is a different idea, and actually it's quite a deep idea. It's there in physics and not in mathematics. It is to absorb infinite quantities into experimentally measured quantities like the charge of the electron, mass of the quantity of the electron. So it's a different notion. And the ultimate of this is something called the renormalization group, where you promote the idea that all our experiments are done at low energies, and stuff that happens at very high energies is really beyond our ken in a very deep sense of the term. So we start out with quantities which are defined at high energies and see what is the low energy effect of that. So that is roughly the program of renormalization. All these are very advanced topics, and I would hesitate to go any further in this direction.
Okay, thank you, Professor Sam. Next question is by Saurav. He's asking, is there any connection between divergence series and non-perturbative physics?
Yeah. Actually, that's right. So most of the time, the problems that we can solve, like quantum electrodynamics, are done perturbatively. That is to say, you have a small parameter, which in this case of QED, quantum electrodynamics, is 1/137. And you can come up with a series expansion in that. And you're able to do the calculation simply because the parameter is small. But there are other theories like quantum chromodynamics, where the expansion parameter is not small, where the perturbation series is not good. Right? And you cannot function as well as in those theories as you can do in QED. So most of the successes of renormalization theory are done in perturbative physics. There are many people who believe that gravity is essentially non-perturbative and cannot be dealt with in the same framework of perturbative gravity. Which turns out to be very hard. Quantum gravity is the hardest problem going. And there are very few, well, there are no experiments except possibly the observation of the cosmological constant, which might be related to quantum gravity, as I was saying. And it's a very difficult field. So let me just stop there.
Thank you, Professor Sam. So I'll now touch upon the math questions, which I have been sort of neglecting. Anyways, so there are a few questions. Sam, you need to help me in understanding these questions. But anyways, Kishan says that I got another solution for the infinite series, which gives the answer -1/8. I think if there is a divergent series, we cannot do work like addition and subtraction.
Yeah, that's right. There are some rules you have to follow to manipulate. So there is a certain grammar for the manipulation of infinite series. And if you follow the rules, the ones I was following are some valid rules. If you follow the rules, you can get only one answer. Because if you can get two different rules, two different answers by following the rules, then you have a contradiction. And that, as I told you, is the mathematical equivalent of a train wreck. Because you can prove any theorem and its alternative theorem.
Okay. Thank you, Sam. So next question by Farooq. Farooq is asking, how do we judge which convergent series is allowed while doing mathematics? Or where can we use and where we cannot use them?
If you open any book on series, there's a section which is full of Cauchy sequences and all that. It tells you the rules by which, when you can perform what manipulations. For example, absolutely convergent series, you can differentiate under the integral, under the summation sign. And there are rules that are clearly laid out that tell you what rules are allowed and what manipulations are allowed and what are not. For example, there are some instances where you can get different answers by switching the orders of summation and integration. So you have to be careful about what you're doing. And if you're dealing with convergent series, there's a famous theorem called Fubini's theorem, which tells you that if you're dealing with convergent and positive quantities, you're okay with many of these things. Let me also say that many physicists manipulate series with gay abandon. If they get into trouble, they go back and look at the mathematics books. And it's a bit like when you were growing up, your parents probably told you don't eat food off the streets. But I'm sure that you and your friends have often eaten food off the streets. And when you get a tummy upset, you go and confess to your parents, and then you start following the rules a bit more. I know that I've done this at the railway station in Jhansi, eating street food off the railway station. But at that time, I didn't fall sick. But there's also the rewards. You might find that you get some very good food that your body is able to stand. In the same way, you can be adventurous, violate some of the mathematical rules, and perhaps get creative with the physics.
So the next question is by Sukalpa, and he is asking, are the values of all divergent series of the form infinity -1/12, something like infinity plus a value?
Yeah. So in the method that we were using a regulator and writing the divergent series as a sum, and then recognizing that the infinite part could be represented as an integral. So it's always the difference between a sum and an integral. So the difference was the finite part of infinity, which was the title of the talk. And infinity was the integral. And that was the part that came into its own only when we started talking about gravitation.
Okay.
So all the Casimir experiments in the laboratory, we threw away that part and looked at the finite part of infinity, which, as someone observed, is all you can see in non-gravitational laboratory experiments.
Okay. Thank you, Professor Sam. So Zaid has a question. What was the intuition that Ramanujan himself had for this infinite formula?
Yeah. Actually, it is not very easy to guess Ramanujan's intuition. See, firstly, he was extremely intuitive. And also, let me just say another thing, that Ramanujan had no interest whatever in physics. The fact that many of his formulae are used in physics today, all over the place, is a complete accident. He himself had no interest in physics. In fact, he had no interest in any subject but mathematics, and he was completely absorbed in his mathematics. And he was so absorbed that he lost his scholarship by failing all the subjects except for mathematics. His intuition is masked by several features. One is that he believed that the goddess of Namakal was a divine inspiration, because his ideas used to just come to him from his, his subconscious mind. And he never used to write down. He's very short on paper. So he would work on a slate, and it's only very, some finished products that he used to put into the pages of his notebooks. Yeah. So a lot of the calculations that led him to develop this intuition are simply missing from the record. So we really don't know the intuition. There are people who've studied Ramanujan's notebooks. There are many, many things which are true, many things which are untrue. And even the mistakes have interesting stories behind them. So he was obviously violating many of the rules. And for example, he did not know complex analysis. He had not independently discovered complex analysis. That education came when he went to Cambridge, and he was exposed to mathematics in the modern form. People like Hardy and Littlewood taught him complex analysis. And of course, then he was very much involved in the circle method and partitions and stuff like that. Okay. In this, there's a parallel with another great mathematician called Bernard Riemann, who formulated this idea of the Riemann, Riemann Zeta function. So he worked on the Riemann Zeta function, and he also used to develop a lot of intuition by very detailed calculations. And his notes were full. He had computed a large number of zeros of the Riemann Zeta function, and finally came up with a conjecture that all the non-trivial zeros, there are some known zeros of the Zeta function, all the non-trivial zeros happen on the line where the real part is half. That is halfway between the imaginary axis and the part where the series diverges. I mean, the power series diverges. Now, that conjecture was probably supported by a large number of calculations, large number of actual computations. Now, what is unfortunate is that, Riemann was very poor. And finally, he had a nervous breakdown, and he had a breakdown of his health. And he passed away at a very young age, about 39 or 40. And after his death, the housekeeper didn't know the value of his notes. And she just burnt all the notes which were there in the room. So we've lost the intuition that Riemann also had. And Riemann, in contrast to Ramanujan, was interested in physics. He had a serious interest in physics. And he has actually anticipated Einstein in saying that the space at least might be curved. And we've lost a lot of valuable mathematics because of this unfortunate historical circumstances. I don't blame the housekeeper. She didn't know any better.
Thank you. Thank you, Sam. So Dinesh has the next question. He asked how to visualize -1/12 part. Can we imagine it as true, but in some other number system?
No, but you can geometrically realize it if you draw a curve of the integral and you draw the series as a set of rectangles. So the area between the curve, which is the integral, and the series of rectangles, that adds up to -1/12. Is that clear?
Yeah.
So the other numbers, there are many other number systems. For example, modular arithmetic is a number system, all of which are interesting and applicable. Just to give you another example, just like Ramanujan had no interest in physics, but ended up contributing to physics, Gauss had a lot of interest in physics, but he used to boast that number theory can never be found useful. In other words, number theory is the queen of mathematics, and it's the queen of all the sciences, and not its handmaid or maidservant. It turned out that number theory is being used these days in cryptography. So people who do things just out of curiosity, thinking they'll never be used, end up finding that later, if they could live long enough, that it is being used.
Thank you, Sam. So next question is by Ahana Jain, and the question is: doesn't Ramanujan's proof take advantage of the size of infinity, as ideally in subtracting 4s from s, the nth term of each should be taken?
Or you mean you should write the numbers one under the other?
I'm not able to visualize that, but I can repeat the question.
If you do that, you'll just subtract s from 4s, right? And you'll get -3s on both sides. So you will not gain anything. The the step of shifting it one is intuitive. I agree with that. No, and that's what Ramanujan did to prove his thing. He must have had some basis for writing the sums as he did, and actually, although the series was known earlier, the proof I'm giving is Ramanujan's proof. And also I want to emphasize as an inspiration Ramanujan's contributions to mathematics as well as physics, despite his lack of interest in the latter. So that's why I based the whole talk on Ramanujan's bust and the series which we're talking about today.
Thank you, Professor Sam. So related to the size of infinity, Agnish had a question during the talk. He asked, sir, can we use similar argument while summing bigger infinities with the small one? Like 1 plus 2 plus 3 ... I'm not able to understand these other symbols. I'll repeat the question, Sam. Sir, can we use this similar argument while summing bigger infinities with the small one?
Yeah, actually, see, there's work by people like Cantor who studied different kinds of infinities. So suppose I sum over m, right? Sum over m, and I write down m there. That's the kind of infinity we've been looking at. Suppose I have sum over m and n of m times n. You don't get a new kind of infinity because you can do the double summation in a different way where it amounts to a single summation. So when Cantor studied infinities, he found that the next kind of infinity is much larger than the current kind of infinity. So I think Rukmini will be able to answer this question better than I can.
Rukmini, would you want to comment?
I don't know this. Yeah.
Okay. Thank you, Sam and Rukmini. So I'll move on to the next question. I think we are also almost running out of time. So Pawan has a question. Sir, in Riemann zeta function, if we put n equals -1 over 2 minus half, what happens to its expansion? Is there exist a practical application from this formula?
Yeah. I believe it's used in the calculation of this Bose-Einstein condensation temperature. The zeta of -half. Yes, I think so. I think that's what appears in that formula. That is, if you take a set of bosons and start cooling the temperature, you find at a certain temperature, all the particles congregate in the ground state. And the mathematical sum you have to do is zeta to the power of, zeta evaluated at -half. Depending on the dimension, you get -half or -3/2. It is used in physics.
Thank you, Professor Sam. So there's another question by Chitrak Bhadra. I think you have touched upon this question, but I'll still read it. The series 1 plus 2 plus 3 plus ... till infinity apparently converges outside the set of natural numbers. How can you explain this intuitively, or it firmly depends on looking through the prism of analytic continuation?
Yeah. I would regard analytic continuation as a trick. The counting numbers, the numbers that you grew up with and the ones that you use when you balance your bank account, that's a certain number field. Okay. So for mathematical purposes and for some physical purposes, it may be interesting to look at more general notions of number. For example, congruency. I can look at numbers modulo 7 or modulo 12. Such numbers are also number systems which can be used. But I wouldn't dream of using a number system modulo 7 if I'm counting money. What it means is that let's suppose that you reach, you count 1 rupee, 2 rupees. When you count 7 rupees, it's the same as 0 rupees. That's not a very good counting system, right? We all want to get more and more money, right? So this is not the kind of mathematics you would use for practical counting. So this is a different kind of mathematics where the series is defined by its analytic continuation. It's not meant to be used as natural numbers are for counting potatoes or sheep. By the way, counting sheep is a good way to go to sleep, but you should only count with natural numbers,
Yeah. So thank you, Sam, for this answer. There is a very interesting question, absolutely the reverse of what we have been discussing. ID is quasar supernova. This is the question from YouTube. Can you use physics to prove Riemann hypothesis?
I doubt it. I very much doubt it, because see, all of physics is much more tenuous and on a relatively more infirm basis than most of the mathematical axioms. What mathematicians would accept as a proof would need to use the mathematical rigor. To be precise, it would need to use Gaussian rigor, which is a very high standard of rigor, which we don't seem to have in physics. We work at a lower level of rigor. There's a trade-off between rigor and relevance. You can do things very rigorously, but if you can only compute, let's say, the motion of the solar system, you cannot do any physics beyond the solar system. It's not very useful, because there's a lot of interesting physics beyond the solar system which cannot be addressed at the same level of rigor. So the skill in theoretical physics is finding the right level of rigor to meet the problem that you want to solve. Yeah. So even in mathematics, this is considered a very hard problem. And one very famous mathematician called Atiyah, who passed away recently, towards the end of his life, he believed he had solved the Riemann hypothesis. But apparently his colleagues don't agree. So it's a very hard problem. And it's one of the problems which is, if you manage to crack it, you will get $1 million. And I think that's in real money, not in modulo arithmetic money.
Thank you. Thank you, Sam. So I'll take this last question, and then I think we can end the session.
Yes.
So Yashwant Singh has a question. Can you repeat the wide open problem that you mentioned during the talk? Yeah. So what is that wide open problem that you were referring to?
That's right. So see, the problem is that you start from the Casimir effect, and then you put in the idea that space-time itself is discrete, and the Casimir energy actually gravitates. And you're led by very simple steps, not very complicated steps, to the idea that there must be a repulsive force in the universe. Apart from attractive gravity, there must also be a repulsive force in the universe coming from vacuum energy. And this is basically, it would have been infinite but for the fact that there's a finite atomic nature to space and time. And it's widely believed that the space-time is not a continuum, because if it is a continuum, these quantities are infinite. But there's a finite cutoff coming at the Planck length, which is the length at which gravity comes into play along with the other quantum effects. The scale of quantum gravity is the Planck length, which is like 10 to the 35 meters. Now, if you use a regulator, which takes that value, what you find is that you predict that the universe has a huge repulsive force. So the second observation is that by looking at supernovae and the recession from us, astronomers have concluded that the universe firstly is expanding. That has been known since the 1920s. But now they've decided that, they've decided on the basis of data that is also expanding. This is in accord with the theoretical prediction. What is not in accord is the size of the expansion. The size of the cosmological, there's a quantity called the cosmological constant that was introduced by Einstein, and which is now revived in modern physics. The size of the cosmological constant turns out to be 10 to the power of minus 120 times the constant predicted by the Casimir argument. This is called the cosmological constant problem, and there's a lot been written about it. If you just check, if you type this into Google, you'll get more than you can read. Well, there's a lot of good writing, some of it by Weinberg. So the problem is, why is the cosmological constant so small? Why is it not as predicted by the theory? This is probably the biggest discrepancy between theory and experiment. And if you want to know where the action is in physics, you should look for where there's a discrepancy so that you can try to understand it. This again is a paradox. As I told you earlier, a paradox is a truth standing on its head to attract attention. So it needs the attention of all physicists, especially the younger generation, people who are willing to take risks and stick out their necks and try out a few crazy things. They have to be crazy enough to succeed. And right now, the problem is that we don't have ideas which are crazy enough to explain this.
Thank you. Thank you, Professor. That was really encouraging for our viewers. Thank you for the wonderful talk, Professor Sam. Now I would ask Rukmini if she has any final remarks. Thank you.
Thank you very much for this illuminating talk, interspersed with very nice stories, very interesting stories. Thank you so much. And the questions, some of the questions were also great. So thanks the audience also for the stimulating.
Thanks,
session.
Rukmini.
Yeah.
Audience, yeah, for your attention, and hope that hope my question. Well, I told the stories to lighten the mood. You know, it's there's a lot of mathematics and a lot of physics, so I thought I should put in some stories. And this is the kind of thing that grandmothers do to keep children entertained. I'm rapidly getting to that stage. Okay.
Thank
so
you.
Thank all.
Yeah. Very deep concepts. Thank you.
And very nice questions. Thank you for that. And very nice interaction.